Welcome to the webinar on steel-intensive battery enclosure structures. This particular presentation was jointly delivered at GDIS 2024 by Tom Wormold of ArcelorMittal and Dr. Yue Wang of Cleveland Cliffs. Today's agenda includes a brief project background overview, followed by a description of the baseline aluminum comparator and the steel concept design approach, grades, and gauges. For the sake of brevity, we will only review the results of a subset of the structural performance assessments conducted throughout the project. However, it will be followed by a full performance scorecard and some closing observations. This project was a pre-competitive collaborative study involving the AISI automotive program and its member companies ArcelorMittal and Cleveland Cliffs, working jointly with Isavant as an engineering and analysis source. The key motivation behind this effort was to develop a sustainable and cost-effective steel design concept for a battery enclosure structure that is mass competitive with a given baseline aluminum one with equal or better performance by exploiting steel's strength and ductility. By doing so, underscores steel's value proposition to automakers to ensure that it remains material of choice for future electrical architectures planned for 2030 and beyond. The approach taken in this project was to first identify a current production high-volume aluminum enclosure to be used as a baseline comparator and to secure the relevant CAD data. The available design space for the steel concept was developed by honoring the existing internal packaging of the production battery pack to the best extent possible and all the attachment locations to the vehicle underbody. The structural performance targets, however, were established by conducting a thorough analysis of the baseline aluminum design. In order to avoid impacting the thermal characteristics of the pack, the steel design was to carry over the integrated two-piece aluminum cooling plate design. Meanwhile, convert all other major panels, such as the top cover and the bottom protective shield, to steel. The goal was to meet or exceed the aluminum performance attributes with minimal mass impact and with the knowledge that some reintegration with the underbody structure will be required. That is to say, it does not need to be a plug and play. Ultimately, develop a credible, manufacturable concept that can serve as a blueprint for production executions with the appropriate rebalancing with the body in white. The aluminum baseline enclosure structure was an extrusion-intensive execution which derived its strength and stiffness from the extensive use of multi-cell thick-walled extrusions and the continuous joining methods used to assemble the structure. By contrast, the steel-intensive concept design was developed using section geometry and gauge optimization for good stiffness, leveraged steel-grade strength and ductility for good energy absorption and intrusion prevention, and used continuous joining technologies such as laser welding, gas metal arc welding, and weld bonding to contribute to the overall structural efficiency. As mentioned before, the aluminum cooling plate was carried over into the steel design. However, unlike the baseline where the cooling plate was only attached to the main body along the periphery, in the new steel concept, it was assumed to be also bonded to the crossmembers in addition to the perimeter of the structure to enhance the overall stiffness. In this section, we will examine the key aspects of both the aluminum baseline design as well as the final steel concept with a breakdown of the materials and the masses. This is an isometric view of the aluminum extrusion intensive baseline that we used as a comparator. One key feature to note is this ledge that actually is part of the side sill of the structure. This ledge is actually the key interface between the battery enclosure and the vehicle rocker section. What is shown here is an exploded view of the aluminum baseline CAD. It shows the different components exploded from each other and also shows the material associated with each as well as the calculated mass of each. The top cover plate is an SMC cover plate with a mass of 12.1 kilograms. The main body of the enclosure, which is extrusion intensive MIG welded together, shown here in gray, weighs around 36.2 kilograms. The aluminum cooling plate is actually a two-piece aluminum cooling plate with a lower and an upper. Both of them here shown, and their mass added together amounts to 32.4 kilograms. And then, of course, there's the protective lower panel, which is also SMC with a mass of 10.6 kilograms. If you add all those together, the mass of the baseline concept comes up to 91.3 kilograms. Similarly, here we have an exploded view of the resulting steel concept CAD, showing the component masses as well as the overall mass for comparison with the baseline in the previous slide. Note that both the top cover and bottom protection panel, which were originally SMC, are now converted to steel, while the cooling plate remained aluminum. One key feature to focus on here is, if you remember, the aluminum interface to the rocker was through a continuous sledge that is actually part of the side sill extrusion. In the case of the steel, they are actually discrete brackets that are assembled to the side sill section. Finally, if you look at the total weight of the assembly, the steel assembly weighs about 95.3 kilograms, as opposed to the 91.3 kilograms, which means the steel assembly is approximately 4 kilograms heavier than the aluminum baseline, which is about 4.4% over the aluminum baseline, and as we will see later, with equal or better performance. Before moving into discussing the details of the construction of the steel-intensive architecture, it's worth noting that the FEA model used to evaluate this steel concept performance in the nonlinear load cases is based on the optimization of the torsion and bending stiffness and modal assessments that were performed prior to that in order to ensure proper section size and gauge distribution. As mentioned before, the top and bottom panels were converted from SMC to steel. The discrete side brackets were designed and optimized for side pole impact. The side sill section also was optimized for side pole impact, both from a flanging and internal bulkhead perspective. All connections were modeled as seam welds, MIG welds, or adhesives. Worth noting here, so the big difference really is, instead of just relying on intrusion prevention as perhaps in the aluminum baseline, the steel concept leverages strength and ductility to also manage the impact energy. The steel concept is described in 4 distinct areas: front, rear, center, and sides. In the next few slides, we will highlight the material grade and gauge distribution around these areas. We will note in the next few slides that all the grades and gauges selected are currently available and already in production. In the front module, with the exception of the purple cage that houses some electronics and the energy absorbing brackets underneath it that are actually DP 780 1.5 millimeter thick, the remainder of the components are actually selected to be DP 980. Some of them are 1.0 millimeter and some of them are actually 1.5 millimeter thick. By contrast, in the rear module, most of the grades are actually cold roll 340 with the exception of a few fore-aft brackets shown in red that are actually DP 780. However, they're fairly light gauge. In the middle structure, which is the center structure, you'll note that the forward and rearward cross members are actually Martin-Siddick 1500. The front is 1.0 millimeter thick and the rear is 1.5 millimeter thick. The fore-aft green parts that are shown here are basically CR 340, 0.7 millimeter, and the cross members shown in the middle are primarily DP 980, 0.65 millimeter thick. Then we have a couple of areas where there are side brackets which are actually used to attach the cross members to the side sill inner, and these are DP780s 0.65 millimeter thick, while there are other brackets shown in gray, these little brackets that are actually DP1180 0.08 millimeter thick, and these are little brackets that actually are little stanchions for the attachment of the module. The side structure consists of the major component, which is the side sill. Inner and outer are both made out of martensitic 1500 2.25 millimeter thick, with internal bulkheads that are strategically distributed throughout, and these are made out of 0.8 millimeter DP 980 material. The outrigger brackets, which are the interface to the rocker, are actually a three-piece construction. The top and bottom are DP 980.7 millimeter, as well as the internal component, which is actually an energy-absorbing component, which is also made out of 0.7 millimeter DP 980. As indicated earlier, both the top cover and the bottom protective plate were converted from SMC to steel. The top cover was converted to 0.6 millimeter CR4, and the bottom protective panel, which is the shield, actually is 0.6 millimeter martensitic 1500. Finally, the aluminum cooling plate, which again is consisting of two discrete parts, the top and the bottom being aluminum, has not been converted and is carried over as mentioned earlier. In this coming section, we will just go over the performance assessments, and as indicated earlier, we'll only touch on a subset of the load cases that were considered just for the sake of time. Having said that, here's a list of the typical load cases that are used in the assessment of battery enclosure structures. There is the modal test, which is an assessment of the first bending and first torsional frequencies, and the criteria here is to avoid any interaction with any of the major vehicle modes. There is a crush test, which is application of a quasi-static load through a 150 millimeter diameter rigid pole to both the front and the side structures. The criteria is really no contact with battery modules before you can reach 100 kilonewtons. Then there is underfloor intrusion, which is a quasi-static load applied through a 20 millimeter diameter round impact to the lower panel, which is the protective shield. And the criteria is not to contact the battery modules prior to reaching 35 kilonewtons. And then there is a drop test, which is dropping it from 4.9 meters at a 15-degree angle to ground with a 9.8 meter per second hitting velocity. The criteria is no failures. And similarly, the shock test, which is proof and abuse shock in XYZ directions. And the criteria is really no rupture or permanent deformation. Static stiffness analysis were conducted initially, as I indicated earlier, to optimize section geometry and gauges. Looking at the stiffness and modal comparison between both the aluminum baseline and the optimized steel, you'd note that for the static torsional stiffness measured in kilonewton millimeter per radian, the steel is slightly better. For static bending measured in kilonewton per millimeter, the steel is appreciably better. For the first torsional mode, measured obviously in hertz, the steel and the aluminum are almost the same. And then for the first bending mode in hertz, the steel is slightly below the aluminum baseline. Here you can see a comparison of the animations between the steel on the right-hand side and the aluminum on the left-hand side in static torsional stiffness. Similarly, here is a comparison of the mode shapes between the steel on the right-hand side and the aluminum on the left-hand side in static bending stiffness. And here is a comparison of the global torsional node between both the steel and the aluminum. We note that they're fairly similar in behavior. And finally, this is a comparison of the global bending mode between the steel and the aluminum, steel on the right-hand side, aluminum on the left-hand side. You'd note that the both modes are fairly similar, with a minor difference because, of course, the steel has discrete outrigger brackets as opposed to the continuous ledge that the aluminum construction has. Moving on to the nonlinear load cases, we've selected front pole crush test as an indicator of the performance of the steel construction versus the aluminum construction. The front pole crush test, as indicated earlier, is a quasi-static load applied through 150 millimeter diameter rigid pole, crushing at a displacement of 1 millimeter per second and applied at the most severe location, with the criteria being to not contact the battery modules prior to reaching 100 kilonewtons. This plan view basically shows a layout of the test. You've got a rigid wall, which is actually the support at the rear end of the structure, and then the pole is actually applied in the front in the most severe location. In this case, if you look at it, it's really the pole is displaced a little bit inboard from the fore-aft member to make sure that at least it's the most severe location for the test. This animation shows the pole encroaching on the front end or the front cross member. You will note the energy absorption characteristics of the front cross member as well as the purple brackets that are actually supported by the purple cross member in front. For clarity, this shows the displacement contour of the pole as it progresses towards the rear during the test. This view shows the stress contours and the distribution of stresses in the front during the application of the pole. One key thing to note is that the cross member, which is actually protecting the modules, is fairly reasonable in terms of stresses, so it does protect the modules fairly well. This is kind of an isometric view of the battery enclosure structure, showing the deformation of the cage bracket, which is shown here in blue, and the purple fore-aft crush members reacting against a purple cross member. The deep red shown here is really the module. So you notice that really nothing's touching the modules. One key point here is the lower steel panel, which is, as we said, is martensitic, and the upper CR4 panel, which is the top cover. You'd notice how they are contributing also to the energy absorbing characteristics of this design. And finally, this shows a head-to-head comparison between the aluminum on top and the steel on the bottom. In this particular load case, it's a view from the bottom. You could see the pole. Both images are synchronized. The pole is moving rearward. The top aluminum solution is really dependent on intrusion prevention. So there is really real strength in the members, as shown by the fact that that blue bracket in the middle is really not deforming any. But the steel, on the other hand, takes advantage of the ductility and strength of the material, and you'd see a lot of energy absorption characteristics. So to that point, if you look at both performances, you'd see that the aluminum crossmember, which shown in gray ahead of the modules that are shown in blue, is deforming a little bit. It's kind of bending because it's being pushed by a fairly strong bracket, while in the case of the steel, the modules that are shown in dark red behind the martensitic purple crossmember are the purple crossmember is hardly bending because the bracket and the structure ahead of it are actually absorbing energy. So to summarize, the steel concept managed the front pole crush by absorbing energy through the geometry grading gauge. This is in contrast to the baseline aluminum design where the emphasis was on strength to stop the pole with little deformation. The front pole was applied to the most severe location in both cases, and the steel concept met the required 100 kilonewton crush force with no yielding or excessive plastic strain in the frame front cross member. Battery modules were not contacted in either case. As promised earlier, here's a performance scorecard that lists all the metrics that were considered and the comparison between the aluminum baseline and the steel intensive battery enclosure structure developed within the project. It's noteworthy to mention that this SIBES concept is not refined. It's basically out of the box. We did work hard on optimizing the gauges and the grade and the geometry of the sections to make sure that at least from a spatial perspective it really fits, and then optimizing the grade distribution to make sure that there is that it actually meets all the required nonlinear load cases. But from a refinement perspective, we do expect that with further refinement, especially with a rebalance between the concept of the battery enclosure and the underbody itself, these numbers could improve way farther. However, out of the box, the SIBES structure is only 4 kilograms heavier than the aluminum structure, which is only 4.4%. That is way below 10%, which one would say, okay, I would live with that for a more sustainable and more cost-effective material selection. Bending stiffness and torsional stiffness are both on the positive side. First bending frequency is a little bit lagging, but again, as I indicated, it's not a refined concept. So again, with further refinement, this will probably improve. However, that said, really, when you think about it, with the rebalancing with the underbody, this may not be an issue. First torsional frequency is on par. And then, of course, all the other load cases, both the aluminum and the steel concepts are good. The steel concept that was developed, again, showed very minor stress concentrations in the shock test that could be easily handled through refinement. Unfortunately, because of the time constraints, we weren't able to continue to refine this, but very confident that this could be easily addressed if needed. In conclusion, the study team managed to demonstrate an environmentally friendly steel-intensive battery enclosure that can compete with an aluminum design on mass and performance. It is important to develop the enclosure structure in unison with the vehicle body structure to ensure proper integration, optimize crash energy absorption, and guarantee battery module protection. The wide range of steel grades currently available to automotive engineers allow them to achieve a real good balance between structural performance, manufacturability, and cost. This concludes our webinar for today. If you have any questions, please send them to me, Hesham Ezzat, or Tom Ormald, ArcelorMittal, or Yu-Wei Wang at Cleveland Cliffs at the email addresses shown. Thank you very much for your attention.